All right, so welcome everyone, and I'll quickly do an introduction of Nick, and before that, I'll just give you the protocol that we're going to follow. So Nick will present the talk, and feel free to ask questions on chat, and we'll get to those questions towards the end of the talk. And the plan is after Nick finishes talking, he'll be able to show some hardware in the lab. Hopefully it works out. So it's my pleasure to introduce Nick Hudson, who's a senior principal research scientist at CSIRO's Robotics and Autonomous Systems group. So he did his Bachelor of Engineering degree back in 2002 at the University of Canterbury, and then went on to do his PhD at Caltech. And after a very short stint lecturing at Caltech, he went on to JPL as a senior roboticist, where he spent a number of years there working on a few DARPA projects. JPL was participating, including leading the winning DARPA ARM project, the DARPA ARM team. And after that, Nick joined Boston Dynamics, working on very cool legged robots, and then around the same time is hired into Google as well, as part of Google's acquisition of Boston Dynamics. And then later on, Nick went on to work at Google X, the Moonshot Factory, where he was leading the perception team, mainly focusing on machine learning and manipulation. And then Nick joined CSIRO 2 years ago. And currently Nick is the technical lead for the robotics group, as well as the principal investigator for CSIRO's team participating in the DARPA Subterranean challenge. So over to you, Nick.
Great. Well, thanks for introducing me, Navinda, and Demetrius and Aaron. Thanks for having me talk today. It's really exciting, and I guess what I'm hoping to show or talk to everybody about today, given the context of this workshop, is, the dynamic hexapod that we've been building for the DARPA Subterranean Challenge, and going through why we're doing it, what's working, what's not, how does this system sort of actually deploy in the real world, and how does it stack up against other legged systems, and how do you make platform choices, and how are these things going to be viable in this kind of competition? Oh, sorry, I gotta click. So I think first of all, I'm going to talk a little bit about the history of hexapods at CSIRO. So Navinda's is at CSIRO as well, and they've spent like a decade of research on a lot of different hexapods, and then really sort of deep dive a little bit into the DARPA Sub-T challenge, like what's interesting about it from a legged robot perspective, and then how did we build and design the hexapod for this competition, progress to date, and insights generated from going through this process. So I think, right, so hexapods at CSIRO has been a long-standing research topic, long before I joined. And what you see at the top is there's a whole bunch of hexapods that have been deployed out, around site, in grass, rocks, underground, in people's attics. And the characteristic of these systems, the ones on the top, are they're sort of cat-sized, they're quite small, but they're very stable. They're quite simple in terms of how their control works. Generally around a central pattern generator with limb feedback control. And they're quasi-static, but they can get over a lot of things, especially when you talk about obstacles that are about the same height, body height, as the robot itself. And I think that's really the appeal is, you can do a lot with that kind of leg topology. And there's been some investigations too. So the bottom left photo is Max. It's a 2-meter tall hexapod. They put it out in the forest and stuff around here. Unfortunately, some of the control stuff was a little lower TRL, but the concept was, how big can you scale these things up? And then there's this Amazon bot, which was actually the basis for the DARPA Hexapod, where they took this Hexapod out to the Amazon and deployed it and did some mapping and stuff there. So the guys, this wasn't my work, but the guys working on it, they have a GitHub. So they open source the CPG, the leg controllers. And yeah, the point is this has been, you know, something that has happened for a long time, and really, you know, they're really leveraging this sort of quasi-static large polygon of support for these legs. And the thing for DARPA, right, is when the sort of BA came out, we really wanted to deploy these systems, but they also had to get there fast. So, you know, there's kilometers of tunnel, and, you know, a lot of the other legged systems sort of, you know, like quadrupeds, it's sort of, you know, a design goal of about a meter a second, right, is something that looks pretty good, that can get you there at a reasonable rate. And then when you're there, you know, you can use all the control strategies and the sort of intrinsic stability of these platforms to go over really rough terrain, right? So the goal for DARPA for us was to get there fast, and then when you're there, be stable because you're a hexapod. And so this is kind of a preview of the whole talk, but you can see the dynamic hexapod we built, some early simulator work, I guess, yeah, it going through some grass, and, you know, long story short, we've got it up to about 0.75 meters a second out of our design goal of 1 over the course of about a year. And I'm going to go through, you know, where we're at with that. But again, a large part of this talk is the insights about deploying a hexapod this size and why you will and will not do it, as well as a little bit of the design. So there's an IROS, hopefully it's been accepted, an IROS paper around the specific design of the robot itself, if you're interested in more details of that. But just a little bit of, for those of you not familiar with the DARPA Sub-T challenge, it's basically a multi-team robot explore mission, right? So you can deploy whatever team of robots you want with one operator, and they have to go explore kilometers of tunnel, and you're gonna encounter all kinds of rough terrain, right? So especially at the start, when they put out the BA or the plan for DARPA Sub-T, they really were going through a lot of aggressive natural terrain. And you know, we've done so that the 3 sort of images I'm showing you are, the bottom left is a tunnel event, which we did in August 2019. And that sort of shows you, like, there's, you know, I think there's a 2.5 kilometers of tunnel sort of showing up in the map on the top left. And then in the middle image for urban, which we were just at in February 2020, you can actually see a scan from one of the drones we deployed, and you can see a stairwell and then a vertical shaft. And so the drone went down the vertical shaft, but the robots that we deployed went up and down the staircase, or sorry, just down the staircases in this case, and, you know, to get to new areas. And so these, and then we're going to end up going to the cave. We're not sure when the cave event is. It was supposed to be in August, so like in 2 months' time, but it's been delayed because of COVID-19 and travel restrictions. But that will have even more natural terrain is the expectation, and apparently things like falling rocks and debris fields in it. So really, what we wanted to do is see if we could build a platform that could really attack all of these situations, right? So mud, sand, inclines, really, really loose rock fields, you know, even dynamic rocks, that kind of stuff, where potentially that's going to trip up other types of robots or prevent sort of more, you know, track systems and things like that. And again, there's this distance requirement, right? So it's not just doing it in a room or from the entrance 100 meters in. You've really got to go kilometers. I think the longest we've traveled with a single robot in this competition so far is 1.5 kilometers. That's sort of back and forth, traversing, exploring different areas. So pretty aggressive, you know, deployment set of requirements, which is really exciting. And then I think, you know, pragmatically, because we also were working within a budget, timelines, a lot of pressure on accomplishing things. I'm going to show you the 2 robot teams that we have deployed in competition so far. And the one on the left, I guess you could say we deployed 10 legs, so a quadruped and a hexapod. So you can see the dynamic hexapod, sorry, up here if you can see my mouse, along with a very large track platform and a small track platform, and some drones as well, right? So it's a heterogeneous team. You can deploy whatever you think works for that scenario. And you can see in the urban event here, we actually increased the number of large track vehicles. And the reason we did that is because these vehicles are actually built in Australia. It's company BA5. And they're actually police robots. And they're specifically designed to go up and down staircases. And so when we learned we were going to go to urban, we bought another one of these vehicles, and we did a lot of work with staircases with this vehicle. And I guess ironically, it turns out you have to go down stairwells, and these robots didn't fit down the stairwells. And so I think in hindsight, that was something that hurt us quite a bit. But that's sort of a major part of this talk, like why legs, right? And the other thing is when we're designing this hexapod system, we want it to carry a decent sized perception pack. So all of our ground robots have this common perception system. And by the time you put that on in comms gear and, whatever else you're putting on it, sort of said, yeah, it needs to take about 4 to 5 kgs. We want to hit a meter a second. And, we want to build multiple of them, so it can't be that expensive. And also, right, it's a robot team. It's about a 10-person team, 20% of the effort of the project, something like that seems reasonable. And then we also want to build it really fast, right? And I think what's cool is we did deploy this robot within a year. And, despite, there's a lot of robot products out there now, which is super exciting for legs. So we have a Vision 60 from Ghost. Considered buying several other legged platforms, but I still think it's economically viable and possible for labs and people to build interesting and impactful robots, despite production of legged systems, which I think has actually brought down the price of a lot of associated technologies, which I'll get into next. So if you look at a timeline of systems, right, for us, when we started this project, that was 2018, September 2018, is really interesting because there weren't legged system products on the market that were relevant for this competition, right? So there was the Ghost Robotics Vision 60 early adopter program, which is really their prototype robots. And so and also Animal, I think, was probably the most developed hexapod at that time. And they had this great research program, which we were considering joining into, which a lot of other universities have done. And I believe Marco is going to be talking about Animal, the Animal C, which you can see on the right, in a couple of days, along with Ghost Robotics is talking about the Ghost Vision 60. I don't remember the days they're speaking, but I think they're the next two talks. And so that's really, in my opinion, what we were aware of, at least, that we considered adopting in 2018. And the other thing that was interesting at that time is you could buy the AnyDrive, the Animal actuators off the shelf. And there was also this company Aptronic, which built the ankle actuators for Robonaut, which are series elastic actuators, which we actually bought. So there were two companies building actuators that we found that we could easily use. And as you go to the right today, both those companies have stopped selling those actuators, and they either sell whole robots entirely or legs, or they want to do custom design of legs. And then obviously you see things like, we all know Spot just went from early adopter to being a full-on product. And then Unitrees, they're also talking in this workshop. And I think what's amazing is, they have a $10,000 US robot that looks great. I'm really excited to hear them talk about it. In theory, like it says it has a 5 kg payload, so it might actually meet our spec requirements for this project too. But just the cost reduction over the last 2 years since we've started this project is ridiculous. Like, it is a completely different landscape than when we started this project. And you can see the robots that we actually have on site up the top. So within a few months of project inception, we had an autonomy pack on an early Ghost Vision 60. And this was us qualifying it for DARPA. At the same time, we basically had a very cheap $8,000 track platform. And then I think what's really cool is you can see our Hexapod qualifying for DARPA before the tunnel event just before August. So that's a year into the project with a full-on Hexapod going. And then at the same time, we also had been talking to local system providers, and we've started using this much bigger track platform, which is a highly aggressive track platform in combination with a smaller one. And then this is also a newer, sorry, I think it's the V3 Ghost Vision 60. We have a V4 as part of the early adopter program for that on lab as well, which we've also been playing with. So to me, what I love about this program is it's really, you know, especially as the PI of the program, right? We have a budget, you have a certain amount of engineering effort, and you want to score as many points as possible. Like obviously we love hexapods, but it's forced us to really take a hard look at what's cost effective and what's performant in this type of environment. And also I should say that the Spot robot, JPL, which they won, I think they got the first place in the urban event that just occurred. They deployed 2 Spot robots, and talking to Ali, who's the PI of that project, just under half their points were scored with that robot, but I think they scored the majority of their points with wheeled platforms. And then talking to Costas Alexis, who's the PI of Cerebus, sorry, they deployed animal systems. It was likewise, they scored about just under half their points in the urban event with the animal systems as well. So legs have played a very important part in the DARPA Sub-T challenge, but it's really been these high TRL systems that have been the ones that have really succeeded. So I think, oh, sorry, I gotta click on this. Wait. So why legs? Like, why have we been deploying legs? Why are we still doing it? And I think you can see here's our large tracked robot on the left, right? And this robot kind of blew a lot of people's minds, mine included, about just what a reasonable size tracked robot could get over. And the reality is that I would be astounded if any of today's robots, Spot, Vision 60, anything, could get over something that robot could not. The downside with that robot is its large footprint, right? It is a large immutable footprint, which prevented it going down stairwells. And that was a big deal. Like, it can go up and down stairs, but it couldn't fit through the stairwells here. And so what you can do, these are 2 video feeds from DARPA here. And you can see CTU Crass was another team that did very well in the competition. They had a small tracked robot, and we deployed our own small tracked robot going down the stairs. And those are both very successful robots going downstairs, but especially in our case, that small tracked robot is not very capable going over this extreme terrain. And on the right here, we have our Vision 60 going over essentially the same rock field. And at the end, you'll see it actually gets its legs stuck in between huge boulders. And these boulders are getting up to a half-meter size. But this is something that tracked robot can go over that still poses a problem for legs. But the reality is that legged system can go both down the stairwell, round small spaces, and over the majority of rough terrain, right? So I think that's why legs are valuable in this competition, not because of their raw performance attributes, but just because of their versatility and form factor. I'm sure this is actually probably my favorite slide because it's not often I get to show 3 different hexapods falling over. But these, I'd say, these are 3 different hexapods that, quadrupeds that were deployed in DARPA in different phases. So Team Pluto UPenn deployed Vision 60's entire fleet of them. There's Animal at the top. spot down the bottom. And each of these, you know, we have them on video falling over and smashing their payloads. And the point is, these are the best quadrupeds pretty much that you can buy, you can get. And it's not that they fall over all the time. They're capable of doing an amazing array of things. And as I said, they scored a lot of points in the competition. But falling for them still occurs, and it's generally catastrophic in terms of payloads and expensive items on top, right? So our payload costs about, I mean, in terms of person hours, raw bomb cost, it's probably close to $80,000 by the time you put research engineers screwing stuff together to make these perception units. And if you're basically shipping these things, if we're shipping stuff overseas, we have a limited away team, and you smash your perception head, that robot's out of the competition pretty much, right? So I think the thing that happened with us, right, is we also deployed this hexapod, and we had catastrophic moments with it. So this was back in August 2019. And what you can see is the hexapod, it literally broke its back leg. Like it disengaged its mechanism, like basically the mechanism just disengaged the way we built it. And again, this was like a year development period. But what's important, right, is that it didn't flip over. It lost an amazing amount of control authority, and just, it didn't make progress, but it didn't fall over either, right? It just kept going. And so I'd say the big argument when you're starting to talk about deploying expensive payloads on legged systems, my personal feeling about why hexapods have a role to play is because of this intrinsic polygon of support, right? It's not necessarily when things are going well. I don't think that you're going to beat quadruped in terms of form factor, probably cost of transport. But I think when things are going badly and things are breaking, a hexapod is a lot more margin to keep going, and it's a lot less likely to break all the expensive things you put on top of it. And so I think it's kind of obvious the reason why this is, which is, in this case, you can see in the top right, as this hexapod is moving around, its center of mass is staying within its polygon of support, right? And as we actually get up to a meter a second, the capture point or the momentum of the vehicle will, push its capture point outside the polygon of support. But, if you're noticing, it's actually got these front two legs, right, which are still there. And so even if that robot, dead stops, and it has its front right leg will be up, and it will just tilt forward and hit that front leg. So it's effective, its effective ability to react forces is still present even if that leg's off the ground, right? And so you're really gonna have a tough time making this robot fall over. So I think that's the rationale of why, I think hexapods have a part to play. And obviously I'm a big advocate of legged systems in this challenge. And I think so I'm gonna get a little bit into the design now of this robot, and there's a paper on more detailed design aspects, and then just go through some morphology, what's working, what's not working, where we're at. So I think what's really cool is it's built around these aptronic linear actuators. You could buy them off the shelf. I don't know if they still sell them, but they're coming close to end of life. But series elastic linear actuator, which made packaging it really easy. So all the mass of this robot is, proximal. It's basically pretty well approximated by a point or rigid mass. There's basically no mass distally on each of these legs. And it worked out well because of the type of actuator that you could rapid prototype a lot of the links with different density materials. And you could do this really quickly, which really leveraged well for this competition. And control-wise, again, we managed to get very reasonable rates, reasonably performant walking with quite a simple controller. So what I mean by that is it's really based around a central pattern generator and leg impedance, and sort of a decent understanding of where the center of mass and your capture point is. So yes, you have a contact wrench resolver, and you're looking at what forces you're applying on the environment, but your ability to change the center of pressure with a huge tripod is immense, right? You don't really need very sophisticated control to make this work or walk well. And I think that was really key, because you could get a lot of motion out of this, a lot of performance out of this, without having to have a massive team or the most sophisticated control. And I think this is basically the timeline of where we're at. And so, we basically had our first build pretty soon, so May 2019, just running central pattern generator. And then, so we did a bit more work on, 6 months later, feed forward forces, a slower walk, really understanding where the center of mass was. And then we started doing, a virtual mass control or virtual model control, where you're really, controlling the body height and the forces on it a bit better. And you can see that, okay, we're not at a meter a second, but this is where, so unfortunately, we haven't really been able to do more development since December, because we had to ship out again in February. And then we've been in lockdown with COVID. So this is really the last sort of video we have of the robot at 0.7 meters a second. And I think the future development we want to do is, more state estimation, probably a six-axis VMC, maybe capture point control. But that's a pretty clear development pathway. That's well-established methods. And I think maybe more importantly is well, what's difficult right now for us? So what are the current limitations we're hitting? And the big ones around the actuators and thermal. And I'll get into the morphology as well, because that's quite deeply coupled. But the big thing is these actuators, their motor is actually suspended, right? So it's not rigidly attached to the chassis, and that actually makes heat sinking pretty hard. And when we're running at 0.7 meters a second, the middle legs actually overheat in about 2 to 3 minutes, because we haven't been able to achieve the heat sinking that we wanted to with the current design. This is a newer heat sink that we've been developing, and you can see the difference in terms of motor core temp. Makes a massive difference, right? But it's a design engineering thing. We've got to do more. Aptronic actually recommends using fluid cooling, which is something we were trying to avoid, but in hindsight, we probably should have done. Although I guess that's very debatable. But that's one of the major issues we have. And obviously heat sinking them would help. The other thing, though, that has been really interesting is we could still do it without heat sinking if we changed the morphology of the robot and started looking at things like parallel springs, which would also massively reduce the cost of transport and increase the range and things like that. And so looking at, there's many paths forward, and I think I'll get to the maybe more interesting one next, which is morphology, right? And so a lot of the hexapods we've been looking at, like on the left, have had this rectangular morphology for a long time, right? And this is much more what you'd see in nature, the sort of symmetry you see there. But what was, during development, I think what was very interesting is this much more unnatural or rotationally symmetric design is actually probably the right answer for this size hexapod. And there's a couple reasons for that. And the first one is basically you get equal loading on each leg, right? So the design on the left, the middle legs here take considerably more load in a tripod gait. And these center motors are the ones that are going to be overheating. All the other ones are fine. Whereas this, you're basically distributing the load much more equally, even though this isn't a topology or morphology that you would see in nature, right? I mean, there are starfish and things, but not many things that locomote that look like this. But in terms of robotics, this makes considerably more sense for us anyway at this size scale. And the other really interesting one that I think, we'd evolved this from a previous design that had been in the forest. And the reality is that it's too big. It was too big to compete in the urban event effectively on the stairwells that we were trying to go into. And it wasn't that it couldn't, it can fit through a door, a standard door. But what it was having trouble doing is going down a staircase and then turning right in a U-turn in in roughly a meter type scale. And the symmetric, rotary symmetric size actually reduces the footprint and gives you a lot more footprint area. And the other reason that we had started again with this rectangular morphology is because in theory, it's quite a bit faster. If you look at, okay, where are the legs going and how far and fast do they have to move? It's a faster morphology. But the reality is what we've found with the walking we're doing in tripod gait, especially, is that we could get roughly equivalent speed out of both morphologies and get the form factor advantage on the one on the right. And so and the reason for that is basically the amount of overlapping workspace of each leg. And because opposing legs on either side are basically working in an asymmetric way in terms of the gait, you can't really have if their workspaces are overlapping, the legs are just going to hit each other. And so the two sort of morphologies on the left, this rectangular and symmetric rotary symmetric design, you can see the maximum workspace here, like when you're at a 1.5 meter a second gait. This is where this leg can move, and pretty soon it's going to hit the middle one, right? Which is actually making it slower because you have less range of travel, even though the joints can move further. Just the way the legs are moving, that's affecting your top speed, hitting 1.5 meters a second. Whereas this symmetric design, you can essentially go the same speed because you have your workspaces are considerably more independent. And then, yes, you do get a higher top speed with this rectangular morphology, but you have to lengthen the body and get the legs further away from each other, which just makes it impractical to go through small spaces. So this is something that, as we went through more and more of the challenge elements, going from a rectangular body to this symmetric body makes a tremendous amount of sense, which was not intuitive at all at the start of this project when we were very focused on speed. So this was a critical thing that we found out about 6 months ago, which is really changing where we're going. But I think, stepping back and thinking about, what are the insights that we've gained from building the system and deploying it? And again, I think there's a long history of building systems, custom systems for DARPA challenges, right? Like the last project that I was on at JPL, they built, RoboSimian. So it's certainly possible to go build new systems for these challenges. But I think the interesting one with this challenge is we went in thinking, okay, we're going to have one type of robot that can do everything, right? And that's going to be this hexapod. It's going to be, it's going to be the best thing out there. It can do every type of terrain. It can get there fast. It can be stable. It's going to be reliable. But essentially what we found is, having a higher TRL system, and what I mean by that, right, is that you can buy it off the shelf, actually becomes quite important for this project. And the reason is just how much stuff breaks. And because we're in Australia and the competition's in the US, we can fly out 10 people, which means we don't have a huge maintenance team, right? So being able to buy spares is incredibly important. And being able to do risky things and being able to credit card it rather than having somebody on the team working for insane hours to fix the hardware itself is a really liberating thing. The other reality is the track platforms that we've been using. A local provider for track platforms has really demonstrated to us that track platforms are so much more capable than we thought. A lot of previous research into search and rescue robots has sort of said that tracks fall off in extreme cases. But I think newer designs for track robots have actually gotten a lot better and haven't got as much attention from the robotics community as you might think, or as I think they should. I think another really big one is, since 2018, there are a lot of quadruped products now, like things that you can go out and credit card. The prices are online. So what I mean by a product is I can go to the website and it tells me how much it costs. I know it's going to be there for a couple of years. I can keep buying them. And the other reason that, continuing this hexapod development for sub-T particularly is unappealing is it's actually a lot less engineering effort to just have a heterogeneous fleet. So if you can deploy a big tracked robot and a small tracked robot and a drone, it's very hard to come up with terrain or types of terrain that they can't do together that a more expensive system, a legged system, would do, right? So you can buy 2 tracked robots and a drone for the same price, as a Spot or any other quadruped really. And, is that going to do better or worse for the same price point as a single system? It's a really interesting question. And the experience in DARPA Sub-T for us has been having a more heterogeneous fleet of systems is an easier engineering challenge than having singleton high-performant individual systems. And what you'll find is that essentially, like JPL, a lot of the teams are also doing this. There's a whole array of robots that people are fielding, which is really exciting. And I think the last one is, like, all these legged system products, I think, can go places that our navigation planner can't send them. So I think one of the real problems, the outstanding problems, when you start talking about going through forests or massive boulder fields, is having the autonomy and intelligence and coordination to figure out where to go and how to go over it. Because even though they can go over these boulder fields, they still require some pretty decent higher levels of autonomy to A, understand that you can do it, and B, differentiate commanding them, sending them over a half-meter boulder versus a quarter-meter high boulder, right? So for us, we're trying to, so we no longer think that the hexapod we're building is the right platform for DARPA. I think we're going to continue with the quadruped systems, especially the product ones. But that doesn't mean we're stopping work on that, on the hexapods themselves. And so really, I think the question and the sort of soul searching that we've been doing has been, where do you deploy these systems, right? Where do they make sense? And for a hexapod like this to make sense, it's got the stability, the intrinsic stability of it needs to overwhelm, whatever you can do in software with a quadruped, right? Because they don't have the same type of stability that we're talking about. And, as we saw, like if you jam your leg into a boulder field with a quadruped, it's probably still going to have problems. And likewise, where track systems, larger track systems that are, comparable in terms of what they can traverse over, where can't they go? And I think the 2 cases that are actually quite important to Australia are, forest systems, so bushfire management. How do you get into these types of jungle forests? And we have a lot of eucalyptus forests. They have like a lot of small trees, vines, a lot of things on the forest floor, where I think these systems make sense, where you really can't have them falling over because of fire risk, things like that. And you just don't want to be smashing your payloads. The other one, and the other reason you might not want to bring the track platform there is because they rip up the forest, right? Those larger track systems really do rip up the forest floor. And the other one is more originally where the hexapod work had started, was confined space inspection, right? Like, you know, okay, going up in your roof, looking at joists, going places where humans really can't go because of the form factor, where I think, you know, you're approaching obstacles that are the same size as your vehicle itself, right? And, you know, that's sort of the smaller hexapod work on the bottom there. So, right, that's the end of my talk. But I think as I said, what's been very interesting is going through the progression of taking these smaller hexapods, scaling them up. You know, I achieved a lot of what we set out to achieve with it. And I think there's a very tangible pathway to hit all the performance specs that we set out to do at the start of DARPA. But despite that, right, that's not the reason why it's not an effective platform in DARPA. It's all the other surrounding reasons about all the other technology development that's happened in the last 2 years, the sort of challenging aspects of the competition itself. And, you know, I think having some time off over the last couple of months has really let us sit back and go, well, why are we doing this in the first place? And is this the most effective thing we can do on the project? And is it the most effective thing we can be doing with hexapods? And yeah, these are the conclusions we came up with. So that's me.
Thanks, Nick. Do you know have a go at trying to show some hardware? And please feel free to ask your questions on chat while Nick tries to show us some hardware.
Yeah, if there's any questions, I can answer them now. Otherwise, I'll go show you some of the hardware right now.
Currently, I'm not seeing any questions on the chat. And those who are on the YouTube stream, please feel free to ask questions on the YouTube chat as well. We can see that and we can answer those questions too.
Yeah, if you wouldn't mind relaying those if they come up, Navinda, that'd be great.
All right, cool. Will do.
Well, I'm going to log in here then on my phone and walk over to the lab, and I'll show you guys some of the robots.
I'll stop your screen sharing from here. Let's see if it works.
Oh, would you mind letting me in on my phone?
Hang on. Yep, you should be in. Do you want to check if your video works on the phone, Nick?
Yeah. Probably get some feedback. Can you see me here?
Yep.
Well, I guess you guys can see my lab, and we're still at less than 35% capacity here, so it's pretty empty. But there are a couple people here. I'm just trying to figure out how to turn my video around. Can you hear me okay, Navinda?
Yes.
So just, I guess, as we walk through, these are some of the smaller robots, the smaller track platforms that we've been using. And then these are these larger track platforms. They're actually built in Brisbane in Australia from BA5. So you get a sense of the sort of scale of them, but they're about 80 kgs. And reasonably, you know, we've been working with the company, but very effective platforms for us outside. And then there's Simon. He's going to show us some legs. This is another track platform we've been looking at. And you can see, as I said, we haven't really had a lot of development since February when we've come back. And the lab's been most like in lockdown for a long time. But you can see a lot of the leg components. There's a pile of legs down there. So the answer is no. I can show you videos of those track platforms driving through mud. They don't get stuck. but here's the legged platform we've had. So a lot of the development we've done in the last month really only has been on a single leg, as opposed to the whole system, just because we don't have the engineering support on site to do it. But you can see, I'll come around this side because of the lighting, I guess. You can see the Apptronic actuators in here, right? And they're driving the leg, and it's a very soft, impedance controller. So we do use a lot of feed forward. A lot of the control output comes from feed forward control. But you can see that it's just a repeated Apptronic actuator through the leg. I don't know, are there any more questions about the leg or? Or about Simon or what we're trying to do?
Oh, there's a question from Justin. What's your experience with the importance and with the importance in software versus hardware? You mentioned there is still much to do in navigation, but most issues seems to be hardware for Subti challenge.
Yeah, so I think for DARPA, right? As I was trying to say, having a reliable hardware is very important. So that's what I meant by having high TRL hardware. Like these, we can just buy off the shelf, right? And it's not that they never break, but when they do break, we actually, the local company will just fix it for us. And what we find is the majority of times that we break robots is when our navigation stack sends it, we still send robots into a wall or into a big gully with our navigation stack. So I think it's the higher, I think what wins in DARPA, or what we're really focusing on, is the higher level of autonomy. Like how do you coordinate a fleet of robots? Knowing where to send them, right? Like figuring out where to explore and how to do that, I think is probably going to score more points than a more capable hardware platform, if that answers the question.
Nick, can you see the other questions on chat? There's one from Nathan and from Michael.
I saw Michael's flash up, which was how much system ID did we have to do? There was a fair amount. So we did a lot of it on the leg itself, like on this test bed. But again, we spent a lot of effort getting all of the mass into the body of the robot. And so the majority of the stance force is the weight of the robot, which is a centralized mass, right? Which meant that the system ID could be a lot less sophisticated. And the other reality is those series elastic actuators, like because they measure force so well at the output, there isn't a lot of stiction or friction to really worry about because of their actuator design, which is great. And so yes, we did do system ID on the single legs and did a fair amount of tuning, but no, it was not a very sophisticated set of things to get it to work.
I'll read out Nathan's question. Simplification to a more direct drive motor design philosophy, MIT Cheetah, over torque protection, unitary Boston Dynamics, or is it more in the software such as smart impedance control, leg placement? Do you see things evolving in the next few years on the topic of hardware actuation?
Yeah, so that's a really good question, because I think when we started this process, right, 2 years ago, we had a pretty heated argument whether to use, like, I wouldn't say direct drive, well, because I guess like a lot of the other robots use sort of 10-to-1 ratios, gear ratios on their legs, those sort of mid-size robots, right? So it's sort of quasi-direct drive. And at the time, buying those types of motors, those frameless motors or pancake motors off the shelf with appropriate motor drivers just wasn't a thing. And Apptronic had this sort of all-in-one solution, which was a really good form factor with series elastic for this types of leg. And the other reality is Animal uses rotary series elastic actuators. But yeah, you're right. Like there's a lot of, in the last 2 years, the most common thing is obviously quasi-direct drive systems with better motor controllers, right? A la MIT, a la, Boston Dynamics, Ghost, all that kind of stuff. And if we were going to do it again now, there's even like an open source motor driver, direct drive. You've probably seen that open source quadruped from New York with Ludovic Ringade. That there is a very appealing system that really wasn't present 2 years ago, that I think if we could restart, we would probably be doing something like that.
There's another one. What did tracked platforms do better on than legged platforms in the Subti challenge? One, there is a problem, the payload is safe compared to legged platforms.
Well, the big one, like the biggest one is, if you look at this robot, right, just payload, like, and it sounds kind of obvious, but I've stood on this robot and driven around on it. Like I can stand on this and drive it around. And so we put a drone on it. The engineering effort is trivial because you don't care about weight. And yeah, I think the capability of what it can drive over is very comparable. Yeah. But size is the issue.
There's a bit of an interesting question. What is the control challenge for legged robots? Do you think the current controller in Boston Dynamics Animal is good enough for real world use?
I haven't tried. I don't have a spot. I do really like the sequential composition paradigm that they use, or they say they use. And I think, Animals showed, like, I think both of those robots have been used in real world scenarios, right? So, like, for instance, if you're starting to talk about construction sites, human environments, it's pretty obvious that those robots are capable of doing that. I think the things where I find it a bit more worrying is when you talk about a forest or rubble fields, or we have a big test track out the back with huge boulders on it, and I don't know the answer to that. I suspect they wouldn't do it flawlessly every time.
Another question from Brianna. Do you have a recovery strategy implement in the case of the robot physically breaking during operation? That is, if the limb snaps. If so, what is it? If not, do you have any ideas for a way to handle such a situation?
Yeah, so we did have the limb snap, and essentially what we did is just detected it and sat down. And so that was the strategy we used. And again, that was what that video showed, right? Was we knew something was wrong with it. And it was just a sit down recovery behavior. But I mean, in theory, there has been some research here about, can you get away with using 5 of 6 legs? Can you still locomote effectively? And I guess I'd say the effort to date has been making it not break and making it as performant as possible. But I do think you're right. If you were really going to put this in a critical scenario, you'd probably want to do something like that, where maybe you have a completely different locomotion strategy. One of the other gaits that the team has been using is you have 5 legs on the ground and you move 1 limb. So you can, I think an obvious thing to do with that robot would be to only use 5 legs and step one out at a time. Be something that would be reasonably possible to implement in a short amount of time.
There's another question from the YouTube stream. Have you thought about using variable stiffness actuators where the stiffness could be changed according to the terrain or stiffness requirement?
Yes, yes, we would love to. So especially in the parallel spring, we've done a lot of experiments and thinking around parallel springs. And I think that's a very compelling thing for insectoid stances, right? Because you get a lot of energy recovery, you know, especially if it's like an actual mechanical spring. You can leverage that. People have shown leveraging that to lower your cost of transport, which I think is a very, very exciting area for these types of systems. That we've really only just had some designs and some modeling of it. We don't have any physical systems that you know actually show that, I guess.
Thanks, Nick. Thank you again for the great talk. I think it was pretty good. We got a good Zoom audience, and we had a number of people watching on the live stream as well. And thanks for those who asked the questions as well. And you can continue to engage with us on the ICRA Slack channel. Please ask any follow-on questions we can try to answer. And I think that's almost time for us. Thanks, Nick.
Well, thank you all. I hope that was good, and hopefully you enjoyed some of the insights from what we gathered from DARPA, and really appreciate the opportunity. Thank you.
All right, thank you. See you all later. Bye.